Hi everyone. So today we'll be talking about Faraday's law of induction and how we could use our knowledge from Calculus 3 to derive the equation representing Faraday's law of induction. And the three calculus knowledge that we'll be needing for our application include partial derivatives, double and triple integrals, vector fields, line integral, surface integral, and Stokes theorem, which is not mandatory, but it's in the textbook. And other general knowledge that we'll need includes cross products, derivatives, and more. So before we talk about the actual physics in Faraday's law of induction, it'll be nice for us to have a brief review of basic physics concepts. So in physics, we have these components of an atom, and there's proton and electron. Proton has a positive charge and electron has negative charge. And we know that these two charges that are the same will repel each other. So two protons will repel each other, and two electron will also repel each other. On the other hand, if we have two different charges, they will attract each other. Now, an electric force is defined as the force that a hypothetical proton would receive when placed in a certain place, in like a location. So if a proton is placed next to a proton, it'll be like repelled, and that's how these lines or electric force lines are drawn for proton and electron, because wherever you place a proton next to a proton, a repelling outer force would be exerted. Or if you place a proton next to an electron, a attractive pulling force would be exerted. That's why they look as such in our graph. Now, using our knowledge of electric force, we can define electric field as the following. So, the electric field would be the vector that is given at a specific 3D location that is the same as the electric force on that specific location. So wherever you place a proton and that receives the electric force at that certain location, that would be defined as the electric field vector in that specific location. And using that, we would be able to produce the electric field diagrams, as you see in this in the diagram here in the slide. On the other hand, we all know magnets, and that magnets with two poles that are the same would repel each other, and two poles that are different would attract each other. So using similar concepts as before, we are able to create a magnetic field, or define a magnetic field based on the magnetic force in that specific location. And note that magnetic field will be defined by the vector B, the symbol B.
In addition to those, we also are able to induce an electric field by a magnetic field. And that is today's topic, Faraday's law of induction. As you see in the picture, a magnet is moving through the coil in and out. And basically here what's happening is that a change in the magnetic flux due to the magnet is inducing an electric field through the coil. And that generates a voltage through the coil, around the coil. This is different from the static electric field, which we talked about earlier, in that this electric field is not conservative. In other words, as you move in full circle along the wire, there will have been some work done by the electric field rather than none, and that's why we see a voltage instead of no voltage as the magnet moves through the coil, and we'll more formally define this later.
So a magnetic flux through the coil is defined as a surface integral over a surface that is bounded by a coil, which we usually take as a disk created by the coil. And it essentially sums up the dot product of the magnetic field with each of the infinitely small area vectors of the surface. The equation for magnetic flux is defined as this. And as you can see, ds points out of the surface S and is perpendicular to it, and with magnitude equal to the area of the unit surface. So Maxwell and Faraday, two scientists, discovered a theorem that a time-varying magnetic field always accompanies a spatially varying and sometimes time-varying non-conservative electric field. So based on what we learned in class, a non-conservative electric field means that the curl of electric field is not zero. It turned out that the curl of electric field equals to the negative of the partial derivative of the magnetic field with respect to t. And essentially, it measures how fast the magnetic field is going to change. So we're going to show you an integral form of equation 1 based on what we learned in Calc 3. So we're going to use a tool called the Stokes theorem, which is not required in class, but it is actually in the textbook. So the Stokes theorem requires a few conditions. The first one is that a vector field, E, which is the electric field, defines on a smooth surface S enclosed by boundary C. And the second requirement is that P, Q, and R needs to be differentiable in a region containing the surface. So actually, Stokes' theorem gave us this formula. The left-hand side is the double integral over a surface, and the right-hand side is a loop integral over the boundary. And since we have this formula, we can substitute the left-hand side of the Stokes' theorem with equation 1, and we can get this formula. Also, we're making an assumption here. We assume that S is constant over time because essentially S is bounded by a boundary C, the wire whose shape does not change over time. And essentially we're measuring, like we can measure how E is changed with respect to S. So we can assume that S is constant over time. So we can just pull out the partial derivative and just do a derivative of the whole equation. And this gave us this formula. So by equating the left-hand side and the right-hand side, and also recall how we define a magnetic flux, we know that the left-hand side is actually equal to the negative of the derivative of the magnetic flux. And this one is actually the definition of electromotive force, which is essentially the voltage.
So those two equations have some immediate implications that they describe two different phenomena. Whether the coil is moving relative to the magnet or the magnet relative to the coil, we always see a changing magnetic flux, which induces an electric field through the coil. And that partly inspired Einstein to develop his special theory of relativity, because only the relative motion of the magnet and the coil mattered.
Another application of Faraday's law is the transformer, or what you see inside your smartphone power brick. So whenever you have an AC circuit and you want to change the voltage inside two wires, you can create the structure shown in this image, which is basically a steel core or a transformer core wrapped around by two sets of wires with AC current running through them. Then you, depending on different density of the wrapping of the coil, you can change the voltage you can change the voltage of the current. And this is possible because, as we recall, according to Faraday's law, change in magnetic flux would induce voltage, right? So using this, if we have one wire with changing current running through them, we can induce voltage through the change in magnetic flux, and as a result produce current. So that's how transformer works.
Another application is electricity generation. So the idea of electromagnetic induction can also be used in electricity generation, and here are different ways to design a generator. On the left, we have a cross-section of a linear electric generator, which basically consists of a magnet moving periodically through loops of coil to generate electricity. And on the right is a diagram of an induction motor that rotates. But if one wants to turn it into an induction electric generator instead of a motor, one just needs to rotate the magnets manually to generate some AC current rather than supplying currents to make the magnet spin. So those are just some of the applications of electromagnetic induction and Faraday's law in electricity generation.
Next, we'll show an example problem that uses the equations that we discussed. So here is a magnetic field directed out of the page perpendicular to the plane of circular coil radius 0.5 meters as shown. The field is symmetric with respect to the center of the coil, and it's decaying exponentially according to this equation here, where V is magnetic field in teslas and T is in seconds. We want to calculate in part A the EMF and in part B the electric field of the coil at T equals to 0. So imagine that we're assuming that the screen is the XY plane, and the direction pointing out of the page is the positive Z direction, and that is the context we will be in when we explore this problem. We can also think of this problem as generating electricity through a linear electric generator.
Now, in order to solve this problem, let us first define the set of points on the disk in which we want to calculate magnetic flux is. So the set of points are the set of points inside within the radius of that coil, or more simply, the set of points x and y, in which x squared plus y squared is less than or equal to 0.5 squared. And that's because the radius of our coil is 0.5. And since our disk is flat on the z plane, we can just put a arbitrary c on the z as our z. Now, if we obtain the partial derivative of our r function with respect to x, we'll get the 1, 0, 0 vector. On the other hand, if we get a partial derivative of r with respect to y, we'll get a 0, 1, 0 vector. And when we try to get the normal vector by finding the cross product of rx and ry, we'll get the 0, 0, 1 vector. So using this, we'll be able to find the magnetic flux. So recall that the magnetic field is pointing outwards, out from the screen, where the screen is the xy plane, since the magnetic field is in a z plane, is parallel to the z-axis. So that's why the magnetic field has a vector of 0, 0, 1.5 e to the power of negative 5t. That's because the entire component of the magnetic field is pointing outwards from the screen in the z-axis. Now, recall the definition of magnetic flux. It's the surface integral of magnetic flux. Surface integral of magnetic field vector to the dot with the dot product of s, the surface integral, the surface. And we can use our knowledge of surface integral to simplify the equation into this second form, and then by plugging in b, the magnetic field vector, and n, the normal vector, and finding their dot product, we'll get 1.5 e to the power of negative 5t as in our integral. And then pulling that out, we simplify. All we need is to calculate the area of the disk we want, which is pi r squared, and plugging in the radius, we'll be able to obtain a magnetic flux represented by the equation 1.178 e to the power of negative 5t. Recall that the definition of f is the derivative of magnetic flux with respect to time. So if we use our derived equation of magnetic flux and derive it by t, we'll get 5.89 e to the power of negative 5t. And then plugging in our time, which is 0, we get an amp of 5.89 voltage.
The second part of the problem, we want to calculate the electric field in the circular coil at t equals to 0. So we can think of the coil as a curve C, and we parameterize it in some way as r of t, where t goes from A to B, and r of A equals r of B. This basically means that we go from one point on the curve and travel along the curve in some way, and we return back to the same point on the curve. That's why r of A equals r of B. So by the Maxwell-Faraday's equation, we have the voltage is equal to the line integral of the electric field over the surface, over the curve C. And by the definition of line integral, we get this equation over here. The dot product inside the integral, by its definition, can be reduced to the magnitude of the electric field along the curve times the speed of the curve and cos theta. So here, since the magnetic field is cylindrically symmetric, we can assume that the electric field's magnitude is constant along this curve. And we can assume that the electric field is tangent to the curve everywhere, which makes theta 0. And we can also pull e out of the integral. Then we get e times the line integral from A to B of the speed of the curve, which we recall is just the arc length from A to B of the curve, and that is the circumference of the coil, which is 2 pi r. So we have the electromotive force is 2 pi r e, and plugging in t equals to 0, and with the results from the previous subproblem, we can have that, we get that E is, the magnitude of the electric field is 1.87 voltage over meter, where the electric field is going counterclockwise, and this is due to the conservation of energy.
So to provide a brief summary of our presentation, we use the knowledge in Calc3, for example, like line integrals, surface integrals, and vector fields, and much more. And then we explore the relationship between magnetic field and electric field with an emphasis on the Faraday's law. So we benefited a lot from the Calc3 class. And with the math tools in hand, we are more adept when encountering some physics problem in real life. Thank you.